So in this one, I'd like to talk about message streams. Previous one, we look at message queues. Message streams are slightly different, but they are fascinating. Apache Kafka, one of the most famous tools out there, it is a message stream. So let's understand where message stream fits into the scheme of things and the kind of things that it gives you out of the box, right? Okay, so message streams are very similar to message queues with few differences here and there. To understand it, let's take an example. Let's say we're building medium.com, right? On medium.com, where people publish blogs, let's say what we want to do is every time a blog is published by a particular user, we do two things. First, we index it in Elasticsearch so that we can power our search engine with that, right? And second is we want to do in the users table count plus plus. Basically, the total post that user has written, we want to do plus plus on that. Now, this means that whenever a blog is published, I'm doing two things. Now, how can we build it with message queues? So we add a RabbitMQ over here. Whenever a blog is published, API server makes an entry into the database for that newly published blog and pushes a message in RabbitMQ. From this RabbitMQ, a bunch of consumers, like one of these consumers, can consume that message. And what that consumer does, it indexes it in Elasticsearch and it fires an update query into this database doing total post equal to total post plus 1. Now here, what we see is this consumer is doing two things, not one. So now what happens? The issue with this is, what if one succeeds while the other one fails? Which means, let's say our write to Elasticsearch succeeded, but before we could write to the database, our call failed or our machine failed, the consumer failed. Now what would happen? In such situation, we would see that in search, we see a user has 5 blogs, but the total post count would be 4. And that's wrong. Your data becomes inconsistent, right? Now you would say, oh, okay, if that's the problem, let us do this. Instead of having one queue, what if I use 2 queues to solve that problem? That my API, whenever we are publishing a blog, your API server updates the database. I should draw a line over here. Your API server updates the database and then pushes the message in 2 RabbitMQ brokers. From one RabbitMQ broker, you have search consumers which are updating it in Elasticsearch, while from other RabbitMQ, you have counters who are updating doing count plus plus in your main database. This solves the problem because now even if search workers are down, your count is still there. But if count are down, your search is still working. So in either case, eventually you would always have a consistent state. It may not be strongly consistent, but eventually the total number of posts in your table that it is showing will be equal to the total number of posts that is part of a search engine. That's all. Seems to solve the problem. Wait, but not really. Here, the API server has to write to 2 queues. That is also a problem, because what if write to one queue succeeded, but before it could write to another one, your API server crashed. You are still left with the same problem. It's not that adding 2 queues did not solve the problem, because now the fault that could happen at workers, that is now taken care of. But what about API servers? API servers, because it is writing to 2 places, this leads to another problem. What if one wrote, other did not write? So before pushing message to other broker, it crashed, right? So here, the root cause of this problem is that we do not want to have multiple calls going from anything. It should be just one, which means I should not be writing to multiple places from API server. I need to write from API server just once, but it should be read many times. So it is write to one and read by many semantic. This is where message streams come in. Apache Kafka, AWS Kinesis are the examples of this, right? Okay, now let's understand what message streams are. So message streams are very similar to message brokers with one change. You can have multiple types of consumers which are reading the same message. So what happened in message queue is that message in message queue was sent to only one of this consumer. All the 3 consumers are homogeneous. They do the exact same thing. So it does not matter to which consumer my message goes, or rather which consumer pulls that message and does that processing, all three are doing the exact same thing. But what message stream suggests, it suggests that instead of your one consumer pulling that message, you can have multiple types of consumer getting the exact same message. Let me explain that. Now what happens is, let's say we replace our message queues with message streams. Now from this same message stream, I can have two different types of consumers all together who are consuming those messages. So for example, user writes or user publishes a blog, API server puts one event in Kafka, and now this one event is consumed by both search as well as counter. Right? And then search does its processing and puts it into Elasticsearch. Counter does its processing and updates the database. Here you see how your API server is just writing to one system. That's it, just one system. It is not writing to multiple places. Right? From this Kafka, that same message is consumed by both the search consumers and the counter consumers. Right? Let's understand this more verbally, rather in a very diagrammatic fashion. You'll understand it. So message queues, let's talk about message queues first. In message queues, examples were SQS and RabbitMQ. Now here, let's say I have 4 messages to send, right? Now what happens is, I have 4 messages to send. I have 3 exact same consumers doing the exact same thing. Whatever they are doing, the exact same thing. So now what happens is, when you send a message in a message queue, the message goes and sits in the front of the queue. The second message comes and sits after that, third after that, fourth after that, fifth after that. Okay. Now when my consumer is running, one of the consumer makes a call to this queue and pulls one message out. So let's say my first consumer pulled this message out. So consumer 1 gets this message and it starts processing it, right? Then let's say consumer 3 made a request. It read the second consumer. It started processing it. Then let's say consumer 2 made the request. It read this message and it started processing it. So it does not matter which consumer am I sending my message to. All 3 are doing the exact same thing, right? And then let's say first consumer was done processing, so it deleted the message. So next time it will get this message. Here you see how one message is sent, or one message is read by one consumer, any one of this consumer, and is doing that processing. All 3 consumers are supposed to do the exact same thing, right? Okay. Now let's talk about message streams. In message streams, let's say I have the same 5 events. Let's say 5 blogs published. First, I would get here. Wait. It goes over here. Then second message is there. It goes over here. Third message goes over here. Fourth after that. And fifth after that. And now I have bunch of messages in my message stream. Message stream examples, Kafka, Kinesis. Right? Okay. Now what do I have? I have the consumers that I have. Now I have different types of consumers, which are called consumer groups. So here I have search consumer group. It can have multiple servers. I have counter consumer groups, which have multiple servers. So like this, consider this as one search consumer server, like set of 3 servers doing the exact same search things, or 3 servers doing exact same counting things, right? These are represented by this. Now I have 2 totally different types of use cases that needs to process the exact same event. For example, every time the blog was published, I put one event over here, and I want same blog published event to be consumed by my search service as well and by my counter service as well. Correct? So now what would happen? Messages are lined up in Kafka. Now the idea is that instead of when your consumer, in this first, when your consumer was pulling the message out from it, something similar would happen. But visually, when you are trying to understand it, think of it like this, where your consumers are iterating over the messages. For example, your search service has this consumer. It starts iterating over these messages, consuming one at a time, and so on and so forth. Right? And while this is iterating, You may have your counter service also iterating on the same set of messages, right? And so on and so forth. So here you see how beautifully the messages are there. Messages are not deleted. Messages lie in Kafka forever. You can configure a deletion policy, but best case, the messages lie in Kafka forever. And whichever type of consumer wants to spin up, you can create a new consumer group and they can start consuming messages from the first message itself without having any problem. So they all iterate through the exact same message in the exact same order. This is what message streams are. So here each search consumer can have multiple servers consuming that message. We'll talk about Kafka essentials in some time, but this is what the idea is, that instead of message being sent to that or consumer would still pull the message over here, but visually the messages are still there in the queue. They are not deleted per se. The messages lie in a particular order, the order of insertion, messages lie there, and then your Kafka or then your consumer type or consumer group iterates over them. This is how you can understand the difference between message queues and message streams. The same set of messages in message streams are iterated by different types of consumers, which makes it really fancy for you to build a lot of great systems. That's why you see Apache Kafka seeing massive adoption out there, right? Okay, now because we are talking about Kafka so much, this discussion, let's go a bit more detail into Kafka. Let's understand the essentials. Every single engineer needs to know these essentials of Apache Kafka, right? So we'll talk about it now. And Apache Kafka, the most popular, and I'm not exaggerating, to be honest, it's the most popular Apache project. It's so good because it has solved a ton of problem for enterprises and ensure them that they build very good architecture. So let's talk about Kafka essentials a bit. So in Kafka, what you have is whenever you are pushing a particular message, you are pushing a message for a topic. Let's say you are building that blogging application we were talking about. In that blogging application, whenever a blog is published, you want to push a message. So your name of the topic would be on publish. You can name it anything you like. Let's say on publish is the name of my topic. Each topic in Kafka has partitions. Now assume that this one pipe that I drew is one topic. Within this topic, I have multiple partitions, right? So when my blog is published and I write a message in Kafka, what happens is the number of partitions I provide, the message that I have, the message is hashed. It knows, okay, this is my hash, this is my partitioning key. Depending on this partitioning key, it would pick one partition to write into. Let's say your partitioning key is user ID. So user ID passed through the hash function, gets an index. It would go to one of these three. Because hash function is deterministic, you would always get the exact same value for the exact same input. So all the events, all the messages for one particular user will always go to one particular partition. It does not mean one user equal to one partition, which means if I have million users, I need 1 million partitions. It's more about you have limited number of partitions, hash function modulus of that value, modulus of the number of partitions that you have. So each partition can handle 333,000 users, right? If I have total 1 million users, a third, right? That's what hash based partitioning would do. So here what would happen is for one of this partition, the message would be going and sitting in front of it, right? So this is what happens when you're sending the message. In Kafka, you have a topic has multiple partitions, one partition, and then when you are putting a message, you define that the partitioning key is something, it's part of the message. It reads that partitioning key, passes it through the hash function, gets which partition it should go to, and it goes to that partition. So here I take example of 3 partitions that I have, right? I have 3 partitions over here. I may have 1 million users. So each partition would roughly handle 333,000 users, right? So, but all the messages belonging to a particular user will always go to one partition, which means I can apply any logic if I want to on the consumer side, right? So this is how your messages would go into Apache Kafka, right? Okay. Now from Kafka, now that messages are there in Kafka, now you want to read those messages. How will you read it? So what happens is when you're reading from a message or reading from a topic using consumer, let's say there are n consumers in your Apache Kafka. Like for this Kafka, I have 3 partitions, which means at max in parallel, I can have 3 consumers of a particular consumer group. For example, I have 3 partitions over here. So which means for search consumer, I can have at max 3 consumers running. So for search consumer, I can have only 3 consumers running, which is consuming message from Kafka, given I have only 3 partitions over here. So internally what Kafka does is whenever a particular consumer is consuming from it, it assigns one partition that it can consume from. So let's say this first partition is consumed by first consumer, second partition by second consumer, third partition by third consumer, right? But now you would say, hey, but let's say I spin up 5, what would happen? The 4th and the 5th that I have search consumer, they would not get any message because it's one-to-one mapping between partition and consumer that you are running. So that when one consumer is iterating over this, it would get all the messages part of that partition, right? So parallelism of Kafka is limited by the number of partitions in Kafka for that particular topic. So now if you would want to consume many things in parallel, let's say you want to have 5 consumers, all of them working, you need to have 5 partitions. So you need to change the number of partitions over here on Kafka. Kafka gives you those abilities to increase the number of partitions, FYI, right? But this is what you need to understand, that Kafka is limited by this particular factor, that one consumer can iterate through one partition only. Or rather, let me put it this way. One partition can be consumed by one consumer. Right? Now, for example, if you don't have 3 consumers, let's say you only have one consumer for search. Here I drew 3. Let's say hypothetically you only have one. You don't have any other. You only have one consumer. Now, in that case, this one consumer will consume from all the 3 partitions. Right? That's what would happen. But as soon as another consumer spins up, one consumer will be dedicatedly assigned to this, while other 2 will be iterated by the first one. But the maximum number of consumers that can consume from a particular topic is equal to the number of partitions of that topic, right? Okay, but now, as I said, you can have search consumers consuming from this, and you can also have analytic or your counter consumers consuming from this exact same thing. No problem in that, right? The same set of messages are iterated by different types of consumers, right? And this is essential of Kafka that you should definitely know, right? Just final thing on Kafka essential is, when you are done reading some set of messages, you can commit. You can commit that, hey, I read till this message, and Kafka will store that for you. So that next time when your consumer restarts, it starts from the last committed point, right? So this way, when you consume a message, you are done processing it, you can either mark that one as committed, that I'm committing till this point, that I've read till this message. Now, next time when that consumer starts, due to any reason, if the consumer failed and it starts back up again, it starts from that exact same point, right? This is how you get resumability in Kafka. You don't have to start from utter beginning always, right? You can start from the middle by committing to that. Right? Similar to how in message queues you were deleting after processing the message, here you will be committing after processing the message, because you cannot delete the message over here. Because if you delete, then how would other consume it? Right? But then, does that mean that my Kafka would be storing every single message it ever received? Theoretically, it can. So long as you have enough disk space, you can. So that is where what Kafka gives you is, Kafka gives you an ability to define deletion policy. Let's say you say that, hey Kafka, I set up a deletion policy of 14 days, which means any message which is older than 40 days, daily a job runs and it would delete the message which are older than 14 days. Right? That's what it does. So you don't have to explicitly delete the message. You just commit the message and say, I read till this point. Next time when that consumer starts up, it starts reading from that. But different types of consumers that you have, they would have their own set of checkpoints. Right? So it is possible that your search consumer is just consume 2 message, while your counter consumer is consuming 100th message. Because search consumer takes time processing it, it moves slowly. 1, 2, 3. While your counter is moving fast. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? It's moving much faster than this. But now you see the beauty of this. Every consumer can consume these things at their own sweet pace without having that pressure of getting it done very fast. right? And these are essentials of Kafka. Now, for you to have deeper understanding of it, whatever we discussed, do that on a local machine. Spin up Kafka, put some message, create some topics, create partitions, put the data, and see how Kafka is reacting, how you are consuming data from Kafka. Try increasing the partitions, try increasing the consumers, see what is happening behind the scenes, right? Practice this. Do this, like take this as an exercise. Try to build a very simple hello world on Kafka. Just spin up Kafka locally. Write bunch of Python, Java, whichever language you're comfortable with. Every language has bindings to Kafka. Put messages onto Kafka and then start consuming from that. Change the number of consumers and see how it reacts. Right? Change the number of partitions and see what happens to existing messages. Right? Explore that, because once you get your hands dirty, you will have much deeper understanding of it. But everything that you should have known about Kafka is what I've covered. Right? Kafka, just to reiterate at the end of it, Kafka is a message stream. It holds the message until you ask it, until as per the deletion policy, it would keep the message there and then. Kafka has topics, topics has partitions, right? When you put a message for a topic. On that message, you define a partition key. Depending on that partition key, it goes and sits into one of the partitions, right? Partitions are limited. Let's say 3 partitions, but 3 partitions can handle 1 million unique users, right? So now each partition has responsibility of messages, let's say 333,000 messages, right? Now each different types of consumers can iterate through Kafka at their own sweet pace. The maximum number of consumers that can consume from Kafka is equal to the number of partitions on that corresponding topic. In this case, I have 3 partitions on this corresponding topic. So I can have at max 3 consumers for a particular consumer type. Each consumer type is iterating at its own sweet pace from Kafka. Right? This is the high level overview, things that you should definitely know about Apache Kafka. Right? But again, highly recommend you to do this exercise to build a deeper understanding of it. And this is what I wanted to cover about message streams. I really hope you found it interesting. I hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.